following content is provided by MIT OpenCourseWare under a Creative Commons license. Additional information about our license and MIT OpenCourseWare in general is available at ocw.mit.edu.
Wave equation. So the model for hyperbolic equations. And that word hyperbolic tells me that signals are traveling with finite speed. In this case, the speed is c. And in this case, the signals are only going to the left. The two-way wave equation will travel left and right, but again, finite speed. I emphasize finite speed because for the heat equation, that the speed is infinite. As soon as you change an initial condition, at any later time, you immediately feel the effect. Well, probably small effect, way out. So diffusion travels with infinite speed. Waves travel with finite speed. Okay. Now, and the difference sort of is that the true growth factor G, you remember, the true growth factor was for the wave equation. This is the G that multiplies the exponential e to the ikx in the difference equation, and G, the true G, is e to the I k c t. So that, what I was going to say is that has absolute value 1. Again, a difference from the heat equation. For the heat equation with diffusion, G will be smaller than 1. You're losing energy. For the wave equation, the energy is constant and the wave is just moving. Okay, so it's a little more delicate because we're trying to, this G in the difference equation has to be somehow close to that one, which is right on the unit circle, and yet we can't go outside the unit circle. So here are two methods. We had one method last time that worked. That was one-sided differences, and of course you had to take the difference on the good side, the upwind side, and that was first order, and the Courant-Friedrichs-Levy condition was the same as the von Neumann stability condition, and it was R between 0 and 1. R is this ratio C delta T over delta X that comes in. It comes into the wave equation. Okay, so now we really have to think about better methods, other methods. And here are two. Lax-Friedrichs, which will only be first order. So these are the questions I always ask, and then finally, experiment. I mean, answering these questions will certainly be a guide to what we'll see experimentally, but there's more to learn from actually doing the numbers. Okay, the accuracy, Lax-Friedrichs, will be only first order, whereas Lax-Wendroff will be second order. So, with respect to accuracy, that's certainly better. Okay, can we see that maybe without too much calculation? The notes would have the more details. Can you see, here's Lax-Wendroff, Lax-Friedrichs. So what's the idea of Lax-Friedrichs? You remember the total failure, the complete and absolute failure when we used a time difference there and a space difference there. You remember that gave the time difference that produced a 1 in G, and this space difference produced an imaginary part in G. So we had G as 1 plus something imaginary, and we were outside the circle automatically. Well, Friedrichs thought of a way to get around that. Instead of using UJN here, instead of the backward difference, he replaced UJN by the average of that value and that value. So that both sides now involve just two numbers, UJN, this one, and this one. This one is not used now. And again, still first order, you won't be surprised that this approximation has got first order error. But stability now is back with us and easy to check, because now each new value depends on what old values, just these two, and with what coefficients. So let me just check stability for Lax-Friedrichs. So uj plus 1n, the new value, is some multiple of this guy, the one on the left, and some multiple of this one, the one on the right. And what are those multiples? Let's see, I'm going to move things over to the right-hand side of the equation. So I think there's a half, and then I think there's an r over 2, minus, I guess this is the one that comes in with a minus sign. It's the one on the left. And the one on the right, uj plus 1n, there's a half plus r over 2. Okay. Simple idea. Simple idea, and it has one advantage, an important advantage over upwind, one-sided, that we saw last time. It's not a great method. It's only first order here. If I and you see what you see when it's going to be stable? The coefficients add to 1. Our coefficients always add to 1, right? Because if we have a constant state, this next step should be that same state. It's not going to change. But instead of having the typical 1 in the G, I have it split into a half. So what is G for this guy? G for this guy is this number, 1 minus r over 2, times e to the minus ik delta x, plus this number, times e to the plus ik delta x. You're seeing now the pattern. So I sort of jumped to G without plugging in the e to the ikx, taking a step, and then factoring out e to the ikx. I did it without writing down the e to the ikx. This is what factors out. And maybe a 1 plus r would be more correct. Okay. So stability requires this complex number, which I could write in different ways. The real part there would be a cosine. This would actually be the cosine plus r times the sine, plus ir times the sine. This is really, I could rewrite that as cos k delta x plus ir sine k delta x. I don't know which way you like. Here, this shows you the real and imaginary parts. That makes it nice. This shows you the two coefficients. That makes it nice. And can you see stability? So what is Courant-Friedrichs-Levy, the characteristic discussion, the argument based on characteristics, says what? Stability is going to mean that delta t has, stability is going to happen when r is below 1. It's just like upwind, except that r could also be coming, c could have the opposite sign. Lax-Friedrichs is prepared for c to be positive or negative, because it's not purely upwind or purely downwind, it's both winds. Okay. So, and do you see that if r is anywhere, so this is, the condition is going to be that -1 R is between -1 and 1. And see what's nice about Friedrichs in that case. This number is positive. This number is positive because the 1 is bigger than the R. So each step, and they add to 1. So each step takes the new value as a combination of the two old values, and of course, the magnitude can't be bigger than 1. So under this condition, I have positive coefficients. That's positive and that's positive. They multiply things of absolute value 1, so the sum can't get beyond 1. Or you might like it here. The magnitude squared is cosine squared plus r squared sine squared. And if r is below 1, we're smaller than cosine squared plus sine squared, which is 1. So if I draw just for a moment, if I draw the G in the complex plane, so there's the unit circle, k equals 0 is always there, that's at 1, then these points, I think probably those points fall on an ellipse here, where we go up as high as r, or magnitude of r, and we go left, right as far as this is k delta x equal pi, as far as -1. So it's stable if this is less than 1. Nothing hard. In fact, easy. Two positive numbers that add to 1. Now, I've added a problem in the problem set, and not requiring it to be turned in, but just to mention it here, that whenever the coefficients are all positive, the accuracy could only be first order. So we can't get too far with positive coefficients. First order accuracy is the best possible, except in the extreme case when we're right on the characteristic. So if r was exactly 1, you remember that special case when r is exactly 1 and we're following exactly the line that carries the true information, r is 1, that's gone, and this is just, so if r is 1, then uj plus 1n is that number. And we're just carrying that information exactly. I have to say, again, that that the idea of trying to follow that characteristic is a totally natural one. And I'm not writing down here a method that tries to do that. But it wouldn't be a bad idea in one dimension. You couldn't do it really well in higher dimensions where these ideas do continue to apply. Okay, so that's Lax-Friedrichs. That's Lax-Friedrichs. Okay. So now let me turn to Lax-Wendroff. These are natural ideas, but Lax and Wendroff did it first. They said, well, if I use these three values, all three, then certainly I can get the accuracy up one more because I have one more coefficient to choose. And to see what they did, the easiest way is to write it as a time difference on the left, to see how they matched. All they want to do is match that second term, that delta x squared term in the Taylor series. And because this gives us a d by dt, this will give us a d by dx with centered, so we get extra accuracy there. And the matching that we need is this term. And do you recognize that? What does that term approximate? I hope I've got it right. That term approximates UXX, right? So this is, they've thrown in a term that approximates UXX, and its purpose is to catch the next order of accuracy. And hopefully not lose stability. Hopefully remain stable. So what we're doing now, what Lax-Wendroff are doing, is staying even closer to this curve. And I guess I have forgotten exactly what their curve will be. If I write down G, oh, maybe you could ask MATLAB to do that. Write down the G for this, for Lax-Wendroff. It's got that extra term. And plot absolute value of G. And I guess you might plot it along with the Lax-Friedrichs value. So what am I guessing? Well, I'm pretty sure that the Lax-Wendroff one will hug the unit circle more closely, but it'll stay inside. So can I just... Lax-Wendroff is G closer to 1, at least for small k. At least for small k, that's really where the accuracy is checked, is how close do these Taylor series match. And Lax-Wendroff match better. And they stay inside. That takes a little calculation. It took me a while yesterday to rewrite write out the G, square the real part, square the imaginary part, add them up, and this is what I got. So for Lax-Wendroff, I got G squared is 1 minus R squared minus R to the 4th times 1 minus cosine K delta X squared. And I put in the notes eventually. Much algebra. But it does the job. Because if R squared, so what's the stability condition? It's again this same guy, the same condition, R squared below 1. And again, we could have a left-going wave and a right-going wave. Now you'll say, what's the good of that? Here we just have one wave. But on Friday, we'll have a wave going both ways. So Lax-Friedrichs and Lax-Wendroff can both deal with that. In fact, their stability conditions are the same. And in fact, you may be wondering, why would anybody use Lax-Friedrichs when Lax-Wendroff gives higher accuracy at no real significant increase in cost? So Lax-Wendroff is a favorite. But don't forget, still, experiment has to be done to see what it really does in practice. Because, you know, right now, everything's looking in Lax-Wendroff's favor, with one exception. Lax-Friedrichs, which only used these two coefficients, had them positive. This is positive. This is positive. Where Lax-Wendroff is going to have a negative. Let's see, where will a negative, I think there'll be a negative coefficient in here somewhere. Yeah, probably one of the three outside guys. I know that we couldn't have three positive coefficients and get up to second order accuracy. And now, where do we pay the price for that? Where do we pay the price? Oh, I should finish here. Suppose R squared is bigger than 1. If you accept this calculation, which has a nice result but took a while. If r squared is below 1, then what do I know about g? Suppose r squared is bigger than 1. What can we say from this formula? Does that hit you right away? G, if r squared, this is certainly, well, absolute g, yeah. I've taken the actual g and squared its real part, squared its imaginary part, did all the algebra I could think of, and got this answer. And for the magnitude squared. So the magnitude squared is never going to go below 0. I don't have to think of that. It's just I want to be sure it's below 1. And so all I really want to do is be sure that I'm subtracting something positive there. Okay, am I subtracting something positive? Well, that's certainly positive. And is this positive? Yeah. R squared will be bigger than r to the 4th. If r squared is less than 1, then r to the 4th is even smaller. So this is positive, I'm subtracting something, so g is certainly not bigger than 1, and that's good. Yeah. Yeah, so that formula really makes it evident. And I guess also evident that we're getting some high accuracy. Do you see what's the size of this when k is small? When k is small, if I'm taking the cosine of a small angle, what am I looking at there? If this is a small angle theta, I'm looking at 1 minus cosine theta. That's of what order? Theta squared. Theta squared. And then that's squared again. So that I'm up to theta to the 4th. That's why I'm getting off to a good start here. Okay. So stability we've got. Two-sided we've got. Experiment. Can I just try to draw a little graph of what I think the two methods will do for our model problem, like this model problem of a wave moving along? I want to try to draw it at let's say at t equal to 1, for example. So at t equal 1, the wave should be here. And well, you might say this is totally unsatisfactory. And it is, because I'm just drawing by hand what you can see, and maybe you should. This would be a perfect experiment, and I really could use, for the notes could use a proper graph here. Okay. I think what you see is, well, let's see. At t equal 1, both methods are going to be 0 way out here, and there'll be 1 way out here. And why is that? Because the signal speed is finite, right? This way out here, it hasn't heard about this wave of water. Way out here, it doesn't know that it's not a constant. But the question is, and I guess the thing has moved, so maybe, can I try roughly? So the true wall of water would be that. And I think that what Lax-Friedrichs, so Lax-Friedrichs with positive coefficients will show a smooth profile, but the perfect signal will get spread out. The perfect signal will get spread out. Why is that? Let me just draw a spread out signal. So apologies to do this by hand. I think it's probably going to be pretty centered, but it's going to be spread out. So that, I think, would be Lax-Friedrichs. That's very rough, right? But I really, hearty thanks for anybody who gives me a code that does it and graphs it. But the main point is we have a lot of smearing here. The accuracy is not going to be terrific. Okay. But there isn't any bumpiness. The reason there's no bumpiness is that Lax-Friedrichs has these positive coefficients. So that every value always has to stay between 0 and 1. The starting values were between 0 and 1. At every step, the values are between 0 and 1 because we're always taking a combination of a positive multiple of one value and another positive multiple of the other value, and the two coefficients adding to 1. You know, we're like taking 30% of one and 70% of another, and we're always in between the 0 and the 1. Okay, what about Lax-Wendroff? What are you expecting for Lax-Wendroff? Expecting better accuracy. Expecting, if I were on the ball, I'd have another color. Okay, Lax-Wendroff will be a much better profile, sharper profile. But, you know what the price is going to be? There'll be some oscillation. There'll be some oscillations behind, I think behind, oh gosh, I should know. Forgive me for, I can fix these if you'll tell me how on the next, because I'm not sure that I should know whether they're at both, or whether the oscillation happens at both ends. I doubt it. No, I doubt it. I don't think it will. Why do I not think it will? Because in Lax-Wendroff, the three coefficients, one of them will be negative and two will be positive. They'll add to 1, of course. And so the oscillations which are coming from, like, sometimes a negative coefficient, sometimes a positive, will all be on one side. So only one of those oscillations is in. So this is my picture of Lax-Wendroff with oscillations behind the wavefront. Okay. All right. If you've done any computing, when you see these oscillations, you immediately think of somebody's name, which is Gibbs. And of course, Gibbs, do you remember the Gibbs phenomenon? That comes when you're approximating a square wave, like these, by pure Fourier series. So the classical Gibbs phenomenon is take the Fourier series for a square wave, well, it's smooth, and then truncate that series, cut that series off at 100 terms or 1,000 terms, and Gibbs noticed, and it's always a problem, that these oscillations appear right near the front. So far away, no problem. But and here we really see it only on one side, because we're not doing Gibbs Fourier series experiment. We're doing Lax-Wendroff wave equation experiment. When I say we, I really hope you'll do it, and a few lines of MATLAB will be greatly appreciated. Maybe Mr. Cho can. You could email to him, for example, a code and the plot. Okay. So, what does that tell us? It tells us Lax-Wendorf has got a lot of potential, but this oscillation isn't good. And and how are you going to get rid of it? Well, how do you get rid of bumpiness? You introduce diffusion. So diffusion, heat equation stuff, smooth things out. Wave equations don't smooth things out. This wall of water in the wave equation stayed a sharp wall. But we'll see very soon in the heat equation, diffusion, viscosity, all those physical things connect numerically to a smoother solution, smoother profile. And so that is really a key idea and we'll see it, but it will make the problem not linear. If we want to stay with a linear equation and increase the accuracy, we're going to get oscillation. But if we locate the oscillation, introduce some diffusion in the right place, we can reduce the oscillation. So that's that's where this is what you really have to do if you want good output from numerical methods, even on that simple model problem. You'll have to have this idea of numerical viscosity, artificial viscosity, numerical diffusion, popped in at the right spot. And so we'll see that. Maybe the right place to see it will be for when the equation itself is already nonlinear. That's where it has developed a lot. So when we get to nonlinear wave equations, which isn't far off, that's what we'll see. Okay. So now I guess I have one more topic in this lecture, and that is convergence. How do you show that we sort of know that we need stability? So I guess, yeah, I have to come to the question of convergence. All right. And of course, I have to mention the key result in the whole theory. The connection, so we have methods that are first order, second order, stable or unstable, and then the key idea is this lax, again he enters, lax equivalence there. So this is a little bit of pure math comes into this. And it gives exactly the result we would expect. Stability implies convergence, and convergence implies stability. So that's the two ideas are equivalent, for provided we're talking about a decent problem. For consistent approximation to well-posed problems. Okay. Well, I've got 4 words on the board, 4 key words here. Stability, we kind of know what that means. Convergence. These are the new words, and I'll just, so consistent means that the method is at least first order, that the difference equation approaches the differential equation at a single step. Well-posed means that the differential equation is okay. So, for example, what would be a non-well-posed problem? Well, when we get to the heat equation, if you ran the heat equation backward in time, that would give us an equation du dt is minus uxx. That would be not well posed. That would be not well posed. Or if you tried to solve Laplace's equation, say utt plus uxx equals 0 from initial values, that would not be well posed. But we're dealing with well posed problems. The wave equation, which has the right sign, and the heat equation with the right sign. So our problems are going to be well posed. You can like safely think, okay, we're only talking about consistent approximations to well posed problems, and here's the main point. Okay, that stability holds if and only if convergence holds. Okay, so there's actually two things to show there. How does stability give convergence, and why does convergence require stability? So that instability could not give convergence. Okay. So that's sort of like maybe the fundamental theorem of numerical analysis. The fact that stability, so what is, we better say what stability is and what is convergence. So let me capture these in inequalities, in mathematical terms rather than just words. Okay. So those are the ideas. Maybe I'm going to have to write a little above here, but so what does what's our method? Right. Okay. So I need some notation, and then I'll lift the board, and we'll see what each thing means. So our method, we're allowing any difference method that moves forward in time. There's time. Let me use R for the true operator that takes the function, follows the differential equation to the next time. So I'm going to say that the true u, which is always a small u, at delta t, is some r, something r times u of t, where the approximate guy is some s times u of t. Okay. So R is the true solution. So well posed. So of course, to take, if this is n delta t, then we've taken R n times. So the true solution is R to the nth times the initial value. And the approximate guy is S n times the initial value, and we might as well start out with those the same. Okay. So that's what R and S are. Now we got three ideas here. What does well posed mean? Well posed means that the true thing is bounded. That R to the nth times u is less than some constant times u. These inequalities are sort of part of the mathematics of partial differential equations. I think you've got to take them as not, take them as sort of a reasonable statement that this is energy. You typically will measure the energy. And in our wave equation, C1, the constant C1 will be 1. The energy doesn't change. In another problem, we could allow the possibility of C1 being a little bigger than 1, but think of C1 as 1. Okay. Then stability will be a bound on S. to the nth. Say C2. And again, in our examples, C2 has been 1. This is like, C2 is like, the S to the nth on each exponential is this G to the nth, and G is below 1. So often C1 and C2 will be 1. And then finally, what is this idea of consistency? And this means, consistent means that, so what's consistent? Consistent is comparing the differential equation with the difference equation. It's comparing R with S. And at a single step, they should be close. So at a single step, R minus S, U, that's the, starting with the same U, I'm just taking one step in the differential equation and comparing it with one step in the difference equation. And I would want that to be, say C3, maybe delta T to the P plus 1, is that times some size of U. Order delta T to the P plus 1, or like delta T squared. This would be the usual situation, that when it's stable. So at the moment, then I want to say, if these are all true, then I get convergence, because what I'm now going to do is show that stability implies convergence. It's what we did for ordinary differential equations. This was the local error. This is the local error that I called DE, the discretization error. And these are saying, so this is saying that here's really what happens. So I want to look at the error up here after n steps. So the error after n steps, typical term is, I follow the differential equation, that's U. Then I have this little error DE, which I make at that step, the difference between R and S. And then I follow the difference equation up to the remaining time. What I want to show is that I can track the error and bound it. I don't know if you remember the discussion for ordinary differential equations, but it went the same way. We looked at the new error DE that was produced at each time step K. When we took K steps when we got up to this point with the true solution, we plugged the true solution into the difference equation. It had a little error, and whatever error there was, that got thrown in with other errors and propagated up to any later time n. Am I bringing back what we did there? Or just you can just see that's what we're going to have here. And now how will I express that? Somehow I have to estimate the difference between R to the nth and S to the nth. That's really my problem. Actually, it's a nice problem. Suppose I have a control of powers of R and S, and I know that R minus S is small somehow. How do I show that R to the nth minus S to the nth is small? That's my job. This is the error when I apply it to a starting value U. This is the difference between little u and big U. So what I want to do is split it out into this situation where I just have one R minus S. So look, I think this will work. So suppose I have I think I could start with r to the n minus 1 times r minus s. And then an r to the n minus 2 times an r minus s times an s. Oh, maybe I don't, sorry, this guy is going to carry me. I'd rather do, sorry. Got to do it right, because I want the r's to come first. I want maybe r minus s times s to the n minus 1. And then, sorry, I want r's on the right. Good. Finally got it. So that gives me the r to the nth, but I've subtracted off. So I need an s, r minus s, r to the n minus 2, and so on. Sorry for this bit of algebra in the middle of practical things. But do you see that this is the case where I followed the differential equation up, and at the last step I made an error. This is the case where I followed the differential equation almost to the top. I made an error, and then I had one more step to go with the difference method. See, the s is doing this part. So a typical term will be a power of s, s to some power, r minus s, r to some power. I'm breaking the error at n steps into n different terms, each from the error at one step. This is the error at the last step. This is the error at the next to last step, and so on. Okay, we've got it. Because I just estimate every term. Every term has a power of r, which gives me a C1, a power of s, which gives me a C2, and the discretization error, the one-step actual error, r minus s, which gives me a C3 and this delta t to the p plus 1. And you see that I'm just piling up n of these. So I'm getting n of those delta t to the p plus 1. So the final result will be I'll have n of these delta t to the p plus 1s, and that will be t, n delta t to the p. So that'll be the error. Well, since I went to all the trouble of defining a C1, C2, and C3, those three numbers. So the error there'll be a C1 times C2 times C3 constant there in the bound. Have a look at the notes for that. And let me just conclude with Lax's insight on the other part, the fact that convergence requires stability. So you see that what I've shown is that if we're stable, if I bound these, bound these, bound these, then I have a bound on the error. And that's convergence. The other way is, why, if it's unstable, how do you know it couldn't converge? How do we know that convergence requires stability? And it's a little delicate, so this is the last 30 seconds of the lecture, just to mention this point. Because it's easy to miss a key point here. We've tracked the different, now I'm supposing that the method is unstable, and I want to show that it will fail, right? That's my job now. That's Lax's, other half of Lax's theorem. If it's unstable, the method will fail. There'll be some initial value for which it blows up. Okay. Now you might say, well, that initial value is just e to the ikx. But we didn't follow this point. But if I take it e to the ikx where g is bigger than 1, of course, that is getting amplified a bit. But for that particular e to the ikx, when delta t decreases, so if I have you see this is a k delta x. What I'm trying to say is that for a fixed k, even an unstable method can work. For a fixed frequency k, as delta t and delta x get smaller, these guys, whether they're outside or inside, will be coming down toward 1, and if you're patient, you could see it actually works. So it's somehow the initial function that doesn't work, that blows up, is a combination of frequencies. A single frequency, actually, you move down here and it's not catastrophic in the end. But a combination of frequencies, so that as one frequency moves down, another one is moving into this position, another one into this, there's a typical initial function, and it is disastrous. So that's what Lax had to catch. The notes will use the single word uniform boundedness. Anyway, this is one point where pure math, a kind of neat result in pure math says that if stability fails, then there is some single starting value on which it will fail. That starting value won't be a pure e to the ikx, because it, as we said, actually, in the end, gets to be okay. But there will be a combination of frequencies that'll fail, and so convergence will fail. So that's the key theorem, and I'll probably won't use the word theorem again. But this is one time when it's justified, and when a little sort of abstract functional analysis gives the conclusion that convergence requires stability. Okay, so you'll see that in the notes, and next time we move on to the true wave equation, second order. Thanks.